We're going to be manipulating rates of exponential equations and looking at moving from smaller increments of time to equations that model the growth or decay over larger increments of time. So we'll start with an exponential growth problem. A scientist counts 4 bacteria in an exponential experimental culture. An hour later, the scientist observes there are 8 bacteria in the culture. What functions can be used to model the growth of the bacteria as a function of hours, days, and weeks? So I'm going to start with the function in terms of hours. So I'm going to go ahead and start with saying, okay, let's find the bacteria in terms of hours. And the reason why I'm doing that is because it says we had 4 bacteria. An hour later, we had 8 bacteria. So when we think of an exponential equation, we think of the equation y equals a b to the x, where a is the initial, b is the rate or the multiplier, and x is that exponent. Okay, and so we start with this. It says the scientist counts 4 bacteria. That's his initial count. So I'm going to say, okay, well, so at time equals 0, the scientist says there are 4 bacteria. Now we need to find what the multiplier or the rate is. And this is actually a very easy problem in that sense is, well, we had 4, we went to 8, so we must have doubled it. So if we could check that, we could say the rate is 8 divided by 4, which is 2. Now I say, okay, the bacteria of hours equals to 4 times 2 to the h power. And the reason why I know that is, well, if I was to say, let's start a table, and I said, well, let's look at the hours and the amount of bacteria, B of H, I would say, well, I know at 1 hour, I would have 4 times 2 to the first, which is really just 4 times 2, amount of bacteria. And then if I had 2 hours, I would say, well, I know I have 4 times 2 bacteria, which is 8, but then I'd multiply it by 2 again, because that rate is going to happen again. And if I had 3, I don't know why it's up there. If I had 3, it would continue 4 times 2 times 2. And then for the 3rd hour, it would double again, giving us 4 to the 3rd, or 4 to the 2 times 2 times 2, which is 2 cubed. Now, as we move on to this, since we've written the equation for bacteria based off of hours, we can actually go ahead and move to bacteria based with days. So let's say I got to 16 hours. Well, as you notice, let's just say I just jumped down to 16 hours. Well, I would have to do 4 times 2 times 2 times 2, and I would do that until I got all the way to 4 times 2 to the 16th power. And if we go to Desmos, we realize really quick that when I type in 4 times 2, 4 times 2 to the 16th power, that number becomes really, really big. And if I had to go to 24 hours, it becomes even larger. And if I had to go to like 36 or 48 hours, these numbers become super duper big and they become really difficult to work with. So as a result, we're going to manipulate that rate. We're going to manipulate the exponent in this case. We're going to say, well, if I went and I said, okay, well, we started with 4. The rate has been 2 the entire time. And if I had to go all the way to 24 hours, I really would just write 4 times 2 to the 24 power. And that would be that part. Well, that would be great if all I wanted to do was have 1 day. But what if I wanted 2 days and 3 days and 4 days? Well, if I wanted 2, 3, or 4 days, well, all I'd be doing is doubling the 24. 2 days would be 48 hours. 3 days would be 72 hours. So what I'm going to do is I'm going to say 24 times the number of days. So notice what's happened. In the original problem, we started with 1 hour. And then to make equation for the number of days, we had to say, well, there's 20, the original rate, but there's 24 of those in one day. So what if we were to go and change it to B of weeks, B of W? Well, we know we started with 4, and we already know, just based off of the Desmos, that if I go to weeks, the numbers are going to get so substantially large, they're going to be impossible to write down. So I'm going to say, okay, well, we started with the original, which was 2. We know that there's 24 hours in one day. And now I want to transfer this to weeks, and we'd say, okay, well, 24 hours times the number of days, but how many days are there in a week? Well, there's 7 of them. So we can scrap this, and I can say, okay, well, there's 7 of them. And that would give me 1 week. But what about 2 weeks? Well, then this whole value right here would double. What about 3 weeks? This whole value up here would triple. What about 4 weeks? Well, this whole value would quadruple because we'd be multiplying it by 4. So instead of doing that, what I'm going to say is, instead of saying all those steps, I'm going to say, well, we have 24 hours in one day, which is right here. We have 7 days in 1 week right here. And then I'm going to add on the fact that we could have any multiple of weeks. So then when I write my equation, B of weeks, I can say, well, 4 times 2 times whatever 24 times 7 is. Let's throw that in the Desmos. 24 times 7, which is 168. And I could say there's 168 hours per week. And now I've modified this equation to have be set up for weeks, a function based off of weeks of the bacteria. I've come here and I've modified it to have a function for days. And I've been able to come back here and originally start with the hours equation.